Okay, so this is 4.1, the fundamental counting principle. So chapter 4 now is all about different ways of counting. Okay, now I know what you're thinking. I already know how to count, Mr. Weber. Thank you. But this is for things that are bigger than your 10 toes and 10 fingers. All right, these are large-scale events. This is how we do large amounts of counting. This is how we know like things like how many stars are in the universe. How many different ways can a person win the lottery? You know, this is looking at larger events and figuring out how many different possibilities there are in the end. And what it starts with is the fundamental counting principle. Now, I know this sounds silly, but the fundamental counting principle is actually one of the most important principles in math because it allows us to do a lot. It's very powerful. So, the fundamental counting principle is if there are X ways to perform one task, and Y ways to perform another, then that is my if-then statement, just like chapter 3. Then there are X times Y ways to perform both. Tasks. Okay? So, what this actually means is, let's say you have a number of ways to perform one thing. Like, let's say you have 3 shirts to choose from to wear today. All right? And you have 2 pairs of pants. So what that means is you have 3 times 2, 6 different possible outfits that you can make. And that's what this is saying. And this is really important. Now, this can be for more than just 2 events. Like I just wrote X and Y to give you an idea. But then you can do this for 8, 9, 10, a million different things. And you can multiply them all together and you'll get an outcome. And that'll let you know how many different ways you can do something. All right? So we're going to use this now, this idea of being able to multiply outcomes for certain events together to give us a total number of outcomes for one entire event going on at one time. Okay? So we'll go through some examples here. Don't forget to hit pause if you have any questions. Need to look something up, go for it. This is all on page like 230 to, we're starting basically at page 230 to 236 in the textbook, okay? So if this sounds a little confusing, don't worry, it's not that bad. We actually used to use back in the day much more convoluted and complicated explanations for this because it's so important that we would give like the formal definition of the fundamental theorem of counting, and it just got confusing. So all we're saying is multiply all your events out, and that's your total amount. Okay? So let's look at a couple of examples here. So a luggage lock opens with the correct 3-digit code. Each wheel rotates through digits 0 to 9. So a luggage lock, it's just like those ones you turn, you get the right code, and you open it up. All right, similar to the ones on briefcases, okay? They have little tumblers. So what I like to do when I'm starting out with fundamental theorem of accounting is I know I have 3 wheels, right, that I got to rotate through. So I have wheel 1, wheel 2, and wheel 3. What I do is I like to make dashes so I know how many events I have going on. And then I put down the outcomes for each event. Okay, so for the first wheel, I could choose between any number from 0 to 9. So 1 to 9 is 9 numbers plus 0. I have 10 possible outcomes for that wheel. Then for the second wheel, I have from 0 to 9 again. So I have 10 possible outcomes there. And then for the third wheel, 10 again. All right, now, according to the fundamental theorem of counting, all I got to do is just multiply these numbers all together, and that's how many possibilities I could have for a combination on a luggage, luggage block. So 10 times 10 times 10 is 1,000. Okay, so there's 1,000 possibilities there. Now, this is where it gets a little interesting. How many different 3-digit codes are possible if each digit can be used only once? So again, I have three events going on, and I can't now repeat numbers. So for the first number, I can still choose from 0 to 9. All right, let's say I pick the number 6. All right, but I have 10 possibilities there. Now that I've used a number, I can't use that one again. So I'll just write it out so you can see. It's like 0, 1, 2, 3. All right, those are all my possibilities. 10 choices for the first number. And I use one for my first digit. How many do I have left for the second digit? I now am down to 9. So I use this one up. Then after that, I'm down to 8. All right, so those are my possibilities for each wheel. So I multiply those together, 720 choices now. Still a substantial amount of possibilities there. Now, let's look at another example. How many postal codes are possible to make in Canada? So remember, postal codes, they go letter, number, letter, number, letter, number. So let's count this out. There's no restrictions here. I didn't say anything about repetition. So there's 26 letters in the alphabet. Cool. Now for numbers, I can choose from 0 to 9, which we know is 10. Letters, 26 again. 10, 26, 10. So now you just take those and you multiply them all together. You're going to get something like 17,576,000. All right, so you can see why this is a handy little tool to use, because you can count out 17.5 million different postal codes in 30 seconds. All right, so this is what I'm talking about when we get into larger numbers. Now, what if the vowels are not allowed to be used and you can't repeat any of the letters or digits? Okay, so vowels, I don't know why, but people forget what they are. A, E, I, O, U. Okay, Y is not a vowel. In this class, it's not considered a vowel at all. It's a consonant. All right? And now, so, set up our events. So I have 5 letters that I can't use. So that means I have 25 choices for my first letter. Oh, sorry, whoa, that's wrong. 26 take away 5 is 21. I had that 5 in my brain. So there's 21 choices. Now I have 10 for my first number. Now I've used a letter, so I don't have 21 choices for the next one. I have 20. And then I've used a number, so I only have 9 choices left there. I have 19 choices now for my last letter because I've used 2 up. And I have 8 choices for my last digit. So if we work that all out, we're going to get 5,745,600 different possibilities. So that's how many postal codes you can do this way. There's other restrictions that they have. I don't think they allow zeros and O's to be side by side. And there's some other ones like 3's and E's can look like that as well. So there's other restrictions. This is just an example off the top of my head. Now, let's do some other ones here. So this one here, Bill owns 5 shirts and 3 sweaters. How many options does Bill have if he chooses one shirt and a sweater? Okay. So you can have a shirt and a sweater. So he's got 5 times 3, 15. Now, that's with the word "and" in it. Whenever that occurs, you multiply your choices together. When you have something like this, because you're choosing both of them, right? When you're doing "or," it's one or the other. You're not doing both of them. So whenever it says "or," write down your choices. So for event 1, for a shirt, 5 choices. For a sweater, again, 3 choices. But since you're only doing one or the other, not both, you add. Okay? 8 choices for that one. And that's the difference there. So just be aware of that. Okay? So that's the difference between "and" "or." All right? That's a tricky one to catch all the time. So don't worry. We're going to spend actually quite a bit of time on counting, or you should. It sounds silly, but it just takes practice. And this isn't really something you've done a lot of before. It requires some different types of thinking. There's no real formula to use. You just kind of have to do it and get good at it. So the key is to not overthink things sometimes, as tricky as that might be. All right, so now the next one, a standard deck of cards. Just for the record, I love card questions. All right, there's so many different possibilities that I can ask with this stuff. So make sure you familiar yourself with the deck of cards. There's the 4 suits: ace, hearts. Well, not aces. Whoa. Let's try that again. So you have spades, and you have clubs that are black in color, and then you have hearts and diamonds. They're all red. And just so you guys know, each suit has 13 cards. So there's 52 in total. 13 times 4 is 52. 3 face cards in each. Face cards, that's going to be king, queen, and jack. For this stuff, I won't get too crazy with like ace cards and stuff, but ace would always come before the 2. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen. Okay? So just a quick breakdown on deck of cards. So this example here says, a standard deck of cards contains 52 cards. Count the number of possibilities of drawing 2 cards and getting a black face card and an ace. Okay, so we have 2 events. We got a black face card and an ace. So black face cards. Look at that, we just went through them. We know each suit has 1, 2, 3 of them, and we know there's 2 black suits. So there's 6 all together for that one. Aces, there's 1 in each suit, so there's 1, 2, 3, 4 of those guys. So the number of ways that you could get a black face card and an ace, there's 24 different ways I can have it. Okay? Now, drawing 1 card and getting either a black face card or an ace. So that just changes it to this. So I've already written everything out, so I know it's going to be 6 black face cards, 4 aces. There's 10 different ways of doing it. Now, this next one here is we want to draw 1 card and getting either a red card or a 10. Okay, so the "or" there says we're going to add things up. So let's look at that. So red cards, there's 2 red suits, 13 cards in total. So now what we do is we go 13 times 2. There's 26 red cards, half the deck. Now there's also 4 10s. Okay, cool. So we would add those together. But what we're not taking into account is, with this, with all our red cards, if we were to draw them all out, so we have hearts and diamonds. And you would have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So there's, right, 13 of them times that by 2, there's your 26. Now with our 10s, you know, we have spade, the club, the heart, and the diamond. But if you look, we've already counted it over here. So we've actually double counted the 10s. So what we have to do is we subtract the 2 that we've already counted. And that just becomes now 28 possible ways. This actually comes back to chapter 3 with the set theory stuff. When we were looking at Venn diagrams, so it'd be like number of red 4 10s. Red union 10, right? That's the OR that we talked about before. So that's just your number of reds. We've got 26 plus the number of 10s, which is 4, minus the number of ones that are red and are a 10. Okay? Like you could even draw it as a Venn diagram. Here's your reds, here's your 10s, and there's a little bit of overlap there, those 2 cards, right? So you have to subtract them because they've been double counted. That's a little tricky for some people, and see, all of a sudden counting's not so easy. Okay? And then finally, the last example, how many ways are there from getting to S to H through each, passing through each point at most once? Okay, so what we do is, okay, we got 2 events here. We got to go from S to T first, and then we're going to go from T to point H. So let's count it out. The ways to get from S to T, I have 1, 2, 3 ways. And then I have to go from T to H, which would be 1, 2, 3, 4, 5 ways. And then this would be an AND question because you have to go from S to T and then T to H. You don't go from S to T or you go from T to H. You have to do both. All right? The OR means one or the other, and means both. Okay? So that's that lesson. So if you guys want to try some of these on your own, they're not that bad. I would start on page 235. So now we go 6. 9. Actually, let's go. Six to 16. Okay, cool.